Hello friends, today we are going to discuss about MOSFET. So we are going to discuss about MOSFET. So uh, this is our NMOS and this is our symbol for PMOS device. So purpose of today's lecture is to understand different regions of operation and their equations. Then we will discuss ID versus VGS. Then we will discuss ID versus VDS graph. Then we will discuss output resistance of MOSFET. After that we will discuss transconductance. Of MOSFET. Okay, so let's start. Let's consider NMOS. This is gate, this is source, and this is drain node. Okay, so this device work in three different regions of operation. First one is linear region, second one is saturation region, third one is subthreshold region. So linear region is basically when VGS greater than VTH. VTH is basically threshold voltage, and VDS less than VGS minus VTH. Saturation region, VGS greater than VTH threshold voltage and VDS greater than VGS minus VTH. In subthreshold region, VGS less than VTH, VGS is less than threshold voltage. So let's see current equation ID for all these three regions. So first one is linear region. In linear region, ID is given by mu n cox W by L VGS minus VTH VDS minus VDS square by 2. So this is equation in linear region. Linear region is also known as triode region. So now in deep triode region, ID is given by okay, before that, so what is deep triode region? Deep triode region. In this region, VDS much less than VGS minus VTH. So in this case, we can ignore VDS squared term. We can ignore this term and we can write ID equals to mu n cox W by L VGS minus VTH VDS. So this is deep triode equation and this is linear region equation. Nu n is basically mobility. W by L is width and length of NMOS. W width, L is length of our MOSFET. Now let's see second one, saturation region. saturation region current equation. So ID equals to half nu n cox W by L VGS minus VTH square 1 plus lambda VDS. Okay, so here this lambda is channel length modulation, and basically if we see MOS structure, say this is N plus, this is N plus, and this is silicon dioxide, this is gate, this is drain, this is source. Now what will happen, as okay, so before that, condition for this saturation region VDS must be greater than VGS minus VTH. As we are increasing our drain voltage, say this is source voltage, this is ground, and gate voltage is constant. As we are increasing our drain voltage, and our channel get tapered basically. So initially when drain voltage is less, then our channel is something like this. As gate voltage increase, now when VDS equals to or you can say drain voltage equals to gate voltage, at that time our channel is tapered like this. So when VDS equals to VGS minus VT, it is like this. Now further, if we increase drain voltage, our channel become like this, and because of this our current remains constant, and this effect is known as channel length modulation. So this is ID versus VDS curve. So so this is ID versus VDS curve. Here for some VGS voltage, this say VGS equals to some VGS1, this ID is constant. Now suppose and this lambda depends upon length. Lambda, channel length modulation, inversely proportional to length. If we keep on increasing length, then lambda will come down, or if we reduce length, lambda will go up. So this is something like this. So here in this direction, length is reducing and lambda is increasing, and in this direction length is increasing, lambda is reducing. So if we want constant current for some VGS voltage, then and our VDS is greater than VGS minus VT, so this point, this will be something like this. So this is VDS equals to VGS minus VTH, and if we want constant current, our VDS should be greater than or equal to VGS minus VTH, and we get more and more constant current if we are having high length and smaller lambda. Okay, so now let's see third region of operation, subthreshold. So for this region, VGS less than VTH is threshold voltage.